Okay, so let's start today's seminar. Um, Thank you very much for coming. So today we will talk about, in my opinion, something quite useful. Um, so this is basically a reduction that allows you to solve a lot of so-called small delay reporting problems. Okay, so basically you learn one technique and then you can apply it in many scenarios. Okay, well, let me motivate um, the situation. Okay, um, uh, let's talk about acyclic joints. Um, so we already know from the previous seminars, acyclic joints are so-called easy um, in several ways. Okay, so in general, let's say Q is an acyclic joint, and the input size of Q is denoted using in, right? And the output size of this joint Q is denoted as out. Okay, so what do we know about acyclic joints so far? Okay, by the way, today I will assume this is so-called data complexity. Okay, so what this means is that in this queue, you have a constant size schema graph. Okay, and in turn, what that means is that you have two constant uh, properties, constant size requirements. The first one says you have a constant number of relations, okay? And the second says for every relation, in each relation, you have a constant number of attributes, okay? So this is the scenario we'll be assuming. By the way, this is not to say this is the absolute requirement for today's technique, but I will leave it to you to go from data complexity to this is so-called combined complexity, where um, the schema graph can have an arbitrary size. Okay, so we have gone a long way, come a long way. So I believe this part is already quite straightforward. Okay, so going back to my definition, so here I have Q as an acyclic joint, and this in is the input size of the joint, and this L is the output size. Okay, so just to remind you that the output size is defined as the number of tuples in the joint result. Okay, and the joint result is denoted using this joint here. Okay, cool. So what do we know? The first thing we know is that if you want to compute the entire joint result, you can do it within this time complexity, okay, in plus L. All right, so this is basically the best you can hope for. And you can see it's linear to both the input and the output sizes. Okay, so this is the best you can hope for. You can compute. Okay, you can compute this um, joint result. All right, so that's the first thing we know. Okay. Another thing we know is that let's say I don't want the entire joint result. If I just want to know the output size, in other words, I just want to know the value of out. Okay, and you don't have to pay the out term here, which is also something very nice. Okay, and then in this case, it's even faster. Okay, so in linear time, and then you can get the value of out. Okay, very nice, right? Now another thing, which is something um, something we talked about last time. This is sampling. Okay, but this time it's not going to be one-off computation. So if you look at these two bullets I have already spoken about, you can see that in each case you are dealing with a one-off problem. You see what I'm saying? You run the algorithm once and then you are done with it, right? Um, in the third bullet, this is sampling result. This is a data structure problem. Okay, think about it as a data structure problem. So whenever I say a data structure problem, you should understand two things. First, there is a pre-processing stage. Okay, pre-processing, right? So you spend some time building this data structure, right? And then the second thing you should remember is that there is a query phase. Okay, so the query here is basically saying, okay, I have a sampling request. Okay, I have a sampling operation. So this sampling operation says, I want to draw a uniformly random sample from the joint result. See what I'm saying? So okay, so you can imagine you pretend as if the results already there stored in some array, in which case you can easily take a uniform sample from the array in constant time, right? But this is just saying, you don't have the joint result physically, but you achieve essentially the same effect, is what I'm saying. Okay. So here, in order to describe this sampling result, I should first mention, this is the pre-processing time, which is linear. Okay, linear to the input size, not to the output size. All right, so you pay only the linear cost to linear to the input size, and then every sampling operation, um, you know, is supported in constant time. Okay, good. All right, so these are the I would say this is um, something we have managed to understand through several weeks seminars. Okay, good. Now today we are going to push one step further. Okay, now let's revisit the first bullet. Okay, so if you look at the first bullet, you will say, okay, that's pretty good. That should be the end of the story. Okay, all right. No more discussions, right? Okay, but what if I say, okay, I'm not happy with that. I'm not happy with that. Okay, um, so what's my point, right? All right. So think about this, right? So think about the value of out. Okay, the value of L can be very large, even for very simple acyclic joints, right? So let me give you an example. Say you have AB, that's the schema of one relation, and then you have BC. You see what I'm saying? Okay, and then you can easily construct an instance where every tuple on the left can join with every tuple on the right. You see what I'm saying? And then if I say what is the value of L, it's at the order of in square. Okay, in square. But just so you know, this is not the worst. This is not a terrible, terrible case, because if you want, I can give you more relations. I can give you more relations. Actually, I'm going to do it right here. So let's say A, B, B, C, and then B, D. Okay. And so on and so forth. Okay. So this L can really, really be huge. You see what I'm saying? So this L can be like in to the power of 3, to the power of 4, da, 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 da. Okay, good. And then some people would say, well, this is not too bad either, right? This is not too bad either because you are paying a linear cost, which you have to do anyway, right? And indeed, you have a point, okay? But what if I say, in practice, we don't want to wait that long before getting the first result? You see what I'm saying? Because think about database systems. Think about database systems where we do pipelining, is what I mean. So you can produce one result tuple in the join and then feed this result tuple to the downstream operations, right? So in this case, you don't want to block the pipeline for too long, is what I'm saying, all right? So this is a one practical consideration, okay? Now let me give you another deeper consideration. Okay, deeper. You see, if so here today we're talking about data complexity. Okay, so here out is still a polynomial with respect to in. You see what I'm saying? But it doesn't have to be, right? If this Q schema graph does not have a constant size, and then this out can this power in the polynomial, right? So into the power of something, and that thing will start to be sensitive to the query size, right? So when the schema graph size. So in that case, and then you can see that you cannot say, this is everything is polynomial. All right, so you have to wait an exponential amount of time, probably, before you can get even the first result, right? So do you still feel completely comfortable with the first bullet? Well, now it becomes controversial, is what I'm saying. So whenever you have a problem like this, people would uh, ask the following. Okay, yes, so this out, the value of out could be exponential, could be very large. I mean, even if we're talking about data complexity, it can be, let's say, in square, right? Okay, but what if we want something stronger, right? So what if we say that even though the result is very large, how about we try to achieve a small delay between the reporting of two consecutive results, right? So if you think about it, think about the two motivations I gave you, right? One from the system perspective and the other one from the theory perspective, right? For the system perspective, this is saying, for pipelining, you don't really have to wait a quadratic amount of time before feeding the first result to the downstream operations, right? So maybe you can quickly produce one tuple, and then you just feed the tuple immediately to the next operation, right? And then you go back to computing the next tuple, and then so on and so forth, right? So if you iterate over this idea, then everything seems much better, right? Now, another thing that is even deeper in theory, in my opinion, is you think about the combined complexity I just mentioned, right? So when the query size is not um, a constant, and then you are facing a problem where the total computation time will have to be exponential in the worst case, right? And we don't like exponential, is what I'm saying. So here we will ask the question, yeah, even though the total query time is exponential, can we still prove something polynomial, right? So that would be a deeper question on your mind. You see what I'm saying? Indeed, if you look at things from the delay perspective, and then becomes possible, right? So even though the value of out is exponential, okay, even though the entire algorithm, I mean, any algorithm, it is true that any algorithm will eventually pay an exponential amount of time. However, you are still able to distinguish different algorithms, right? So some algorithms will give you a polynomial guarantee, even though the total running time of the algorithm will have to be exponential. So that's quite interesting, right? So if you think about it, that's one way to study this kind of problems, right? Which kind? I mean, the total amount of total running time will have to be very big. However, are you able to cut everything into smaller pieces? Okay, good. So this is the motivation behind this small delay formulation. Okay, small delay formulation. So before I talk about this small delay evaluation, I want you to um, remember that these are the results we currently have. Okay, so and today I will give you a generic reduction, and this generic reduction will rely on these results. Okay, so next time when you try to apply the reduction, again, you will have to first obtain these results. Okay, so this is something I want you to keep in mind. Okay, all right. Now, so just to let you know that even if you want to achieve a small delay, it does not mean that you are able to forget about everything I have said in the past few weeks. Okay, good. So what's the meaning of small delay here? Okay. Well, small delay in our particular scenario on a cyclic join. Okay. Again, we assume that the schema graph is has a constant size, right? So this says, well, after some linear warm-up time. Okay, so you can think about it as a pre-processing, except that this is not a data structure problem, right? So some warm-up time. Okay, so I give you a slack of linear amount of time. Okay, you don't need to report anything during this warm-up time, initialization time. Okay, but then after this warm-up time, and then you will have to report the first result within, let's say, delta time. Within delta time. Okay, within delta time, and delta is some value, right? Some bound. Within delta time, you will have to do the following. You will have to say, okay, no result at all. okay, the join result is empty, all right? Or you should say, okay, now here is one result tuple in the join. You see what I'm saying? Okay, and then so that's the first round, okay, and for the first iteration, and then you should start the next iteration, and the same delay guarantee applies, which says within another delta amount of time, you should either say no more, okay, so all the tuples have been reported, or here is another new tuple in the join result. Okay, so this is what you have to do in the second iteration. Okay, so you have to keep doing this. Okay, you have to keep doing this again and again until the end. All right. So if this is the case, and then we say that this is small delay. Okay, this is small delay. Well, let me tell you, theoretically speaking, even though you are able to do in plus out, theoretically speaking, okay, not every algorithm able to do in plus L can achieve a small delay. Okay, theoretically speaking. Okay, why? Because think about the scenario I gave you, right? So let's say out is at the order of in squared. Okay, say an algorithm is able to do in plus out, right? However, it's possible for the algorithm to behave like this. Okay, after some initial linear amount of warm-up time, okay? And the algorithm can go silent, you see what I'm saying, for a very long period of time, okay? So let's say this is in squared, okay? Before the algorithm, start reporting results. You see what I'm saying? So this is not to say Yanakaki's algorithm cannot achieve a small delay. That's not what I'm saying. Actually, it can, all right? But that's not the point of today's seminar, as you will see, all right? But this is to say not every algorithm that can promise to do in plus L will necessarily be able to achieve small delay, okay? Because an algorithm can behave like this, all right? Just so you know, right? Okay, so in this case, if you look at my diagram here, what will be the delay? The delay will be actually in square, is what I mean, because only the allowance for you is the initial linear time, all right, the initial phase, right? So after that grace period, and then you should be producing result tuples, right? But if your algorithm behaves like this, and then the delay will be in square. Okay, all right. So before continuing, let me tell you, right? So you can adapt Yanakaki's algorithm, okay, to achieve a constant delay. Okay, today I'm not going to go into that. Should not be too difficult, all right? But this is not the point today. Today we will prove a reduction, okay? And as you will see, this reduction on this particular problem will gain nothing over Yanakaki's algorithm. However, this reduction is applicable in many other scenarios. Okay, so in a lot of other scenarios, this algorithm actually achieves a very good delay, and no other methods are known to achieve that delay. So you can see uh, uh, this is the point of today's seminar. Okay. Well, today I'm going to talk about a separate problem. Okay, this problem is a standalone problem. Okay, so I'm going to give you um, an input. Okay, so this input is a set. Okay, so a set of n elements. Okay. All right. The value of n is known. Okay, so let me write this down. N is known. Now, for the time being, um, 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 you can start a new context, right? You can, for the time being, forget about cyclic joints, right? So this is defining a new problem. So the size of the set is known. Okay, and also we are given two black box algorithms that are able to achieve the following. The first one is you are able to report the whole S. Okay, the whole the whole S in how much time? In S times some function. Okay, let's say this function is lambda report. For example, if you say you can report this S in linear time, big O of n, and then this lambda will be constant. Okay, and if you say you can report the whole S in n log n time, and then this lambda report will be log n. Is what I mean? All right. Okay. I would probably say something like this: n times lambda rep. Okay, so this is reporting. Okay. And also you have another algorithm that is able to sample from S in lambda samp time. Okay, let's say SAM time. Okay, so for example, if you can sample from S in log n time, and this lambda sam will be log n. Okay, so you get the idea. Okay, now what I'm going to do is to give you an algorithm that is able to report this entire S with a small delay. Okay, so we'll be able to do a small delay of lambda rep plus lambda sam in expectation. Okay, in expectation. So what's the meaning of small delay in expectation? So I said before, right? So I said, after some grace period, you should start producing results, right? So in this case, there's no grace period. You will have to, because you can imagine that the grace period is basically for preparing the algorithms satisfying these three bullets. Okay, so no more grace period, and you should start the iterations right away. Okay, so each iteration you should produce a new element until the very end. Okay. And every iteration, if I say it's a small delay in the worst case, and then every iteration will have a strictly bounded amount of time. Okay, so here this is saying that the small delay is in expectation. This says the iteration. If you look at it, if you look at the time, it can be a random variable, and it will be. And the expectation of this random variable will be bounded by the sum of these two lambdas. Okay, lambda rep plus lambda sam. Okay. So for example, if lambda rep is a constant and lambda sam is a constant, and then you achieve constant delay in expectation. Okay. Now, yes.
That's subject no preprocessing.
The preprocessing is for producing the three bullets.
Okay.
Okay. Right. All right. Now there's one more thing. So I'll go back to the preprocessing in a little bit. I will draw connections between this problem and the acyclic join very shortly. All right. But there's a side product of this algorithm. Okay. So as I said, right, one iteration will give you a new element. So if you look at the sequence of elements produced, okay, so what this algorithm can guarantee is that the sequence is definitely going to be a random permutation of the set S. Okay, so you don't just achieve a small delay. In the meantime, you also achieve a random permutation. Okay, good. Well, let's connect the dots, right? So let's see why this is something we need for acyclic joins. Okay, so in this case, I want you to think about this as the result of this acyclic join. Okay, you have this Q, right? So join Q, right? The result is this S. Is that all right? Okay, good. Now you tell me, are you able to satisfy the three bullets in this pre-processing period? Okay, so this initial grace period that I promised you, right? According to the things that you have learned, right? You can see I purposely wrote things in three bullets because there's one correspondence between these three bullets and these three bullets here. You see what I mean? So if you look at the first one, right? So in order to satisfy the first bullet, you have to be able to get me the value of n, but n here should be understood at the size of S, which is the result of the join, right? So the value n here is simply the value out on this page. Okay, so are you able to do it in constant time? Yes, actually it's the second bullet here. Okay, good. Now, if you look at the second bullet here on this page, you have to report the whole thing in n times lambda rep, right? So are you able to do that? Yes, you are able to do it. Actually, this is, you don't even need a grace period for this, right? Because you can directly use the first bullet. Oh, okay, so this is something I have to um, um, provide some supplemental explanation. So we need something stronger than what I said here. Okay, so what I said here is not completely enough. So for Yannakakis, you are able to achieve the following. Okay, you can break these two terms into this form, and you can regard the first form as the preprocessing, and then the second term as just the just for the purpose of outputting. Okay. Now, this is something we talked about several weeks back, and I hope you can still remember this. But here is here is the rough idea, right? So if you think about Yannakakis, right, there is this first step of the algorithm is to produce a fully reduced join, right? A fully reduced version of the join. So what you do is, if you still remember, you root the join tree, and then you do bottom up, and then you do top down, right? So that goes into the first term, is what I mean. And after this, you will be able to start producing the join result, in constant time. You will be producing the result in out time. So there's no more in, in the second phase. Okay. All right, good. So coming back here, in order to satisfy the second bullet, yes, you still need a grace period. So the grace period is this bottom up and top down phases performed by the Yannakakis algorithm, right? So Yannakakis algorithm, after linear time, you are able to report everything in out time, right? So here, if you look at this lambda rep, now remember the value of n here is just out, right? So what is the value of lambda rep? It's bounded by the constant, okay? Now, finally, for the third bullet, this is quite obvious. This is something we talked about previous week. After linear time, you are able to build a structure to support the sampling operation in constant time. So lambda sam here is also a constant. Okay, good. And therefore, if I make good my promise, okay, if I indeed I convince you that there is a reduction that's able to do this, and then combining everything we have learned, what do you get immediately? You immediately for free, right? Get an algorithm that's able to achieve a small delay. Actually, how small? Constant in expectation delay. Okay, for any acyclic join. Okay, even better, you don't just get a small delay, you get a random permutation of the join result. All right. Well, so let me go back to Yannakakis algorithm a little bit. All right. So if you are talking about just an acyclic join, okay, just an acyclic join, if you just want to achieve constant small delay in the worst case, not even expectation, and then you are able to apply Yannakakis algorithm directly. Okay. However, if you want to find a random permutation, then you need much more work. Okay, you need much more work. Okay, so it's not going to be a one sentence solution. All right. However, if you apply this reduction, and then it will indeed be a one sentence solution. Okay, good. Very nice. I hope I have got your interest. Okay, so now we will focus on this problem. All right, so the rest of my talk today will focus on this problem. Okay, good. All right. Well, I promise you will learn something interesting today, because what you will be looking at is something people call de-amortization. Okay, de-amortization. All right. Now, this is something that is quite, I would say, quite let me find a good word here. Uh, Quite intriguing. Okay, intriguing in the sense that it's not trivial. All right. So before, I still remember how I felt when I was first introduced this thing. Before I saw it, I did not believe it. Okay, but after I see it, I said, "Wow, that's so interesting." I mean, this is exactly the kind of feelings I hope I can make you feel today. Okay, good. Now, um, if I directly present the final algorithm, and then I will be convincing, I think I would be convincing many of you. Okay, which is why I would do it in two steps. I'll first give you one algorithm that is correct. That this obviousness. I mean, sorry, this correctness is obvious, but it's not an algorithm we need. Okay, so if you look at the small delay, it can be terrible. But the thing is, after you are convinced that that algorithm works, and then I'm going to convert that algorithm into an algorithm we need using this, so-called de-amortization approach. All right, so it's the de-amortization I want to demonstrate. Okay, good. Now let's start with our solution one. The solution one is really a simple solution. Um, if I say, I just want you to use these three operations, right? What do I mean operations? Look, I give you three bullets, right? So you have the value n for free. So whenever you need the size n, you have it. You get it for free. And then whenever you need to report the whole thing, you can apply the second algorithm and the third, right? So if I say, hey, what I want you to do is to give me a random permutation. Okay, are you able to do it? Then you say, of course you're able to do it. Okay, you have many solutions, right? So for example, one solution is to say, you just get the whole S using the second bullet. You don't even need the second. Sorry, you don't even need a third bullet, right? So you can retrieve the whole S, and then you say you randomly permute it, right? So by the way, how you can randomly permute a set of n elements, right? So I talked about this in my seminar series that was before Christmas. Okay, so I talked about this. Okay. However, now remember the point is not just to compute a random permutation. Okay, the point is to have a solution that can be de-amortized into something we need. You see what I'm saying? All right. And therefore, when you look at the first solution, at first glance, you will be wondering, oh, why do all these things? I mean, why not take a simpler approach, right? But now you have the answer. Okay, good. All right. So the solution has three phases. Okay, has three phases. All right. So the first phase, okay, we're going to produce phase one. Okay, we're going to produce a permutation of n by 2 elements. Only n by 2. Okay, so we want to produce a permutation of length n. All right, but first phase we will only produce n by 2. Okay, so let's see how this is done. Now, before continuing, let me mention a fundamental technique that I will need. So this is called perfect hashing. Okay, dynamic perfect hashing. You don't have to know the details of dynamic perfect hashing, but you should know the result. Okay, perfect hashing. So this dynamic perfect hashing says the following. Everybody knows hashing, right? So if I give you a set of elements, let's say T, right? I want you to create a hash table, and then I can test for membership. You see what I'm saying? I give you an element. I can ask, okay, so is this element, let's say E, in your set T? Let's say the set is a set of integers, right? Everything can be regarded as an integer, right? As long as it can be encoded in a word, right? Okay, so this is hashing, right? But why dynamic? Why perfect? Okay, so dynamic essentially says you are able to support insertions. Well, you can also support deletions, but we don't need deletions today. So you can support insertions. You can add stuff into the set T. Okay, and accordingly to update the data structure, right? But why perfect? Okay, why perfect? Perfect essentially says, if you build a normal hash table, okay, and then when I say I want to test membership, what is your guarantee? So many people will say outright, oh, constant. Well, this is I would say 70% correct. Okay. Why? Because it's not really constant. It's a constant in expectation. You see what I'm saying?
Yes.
All right, constant expectation. But today, this constant expectation is not going to be enough for us. Okay, so we will need something that holds in the worst case. Okay, so that's why perfect. You see what I'm saying? Basically, whenever people say perfect, you can imagine the ultimate purpose is to achieve constant lookup time. Okay, so you no longer have a constant expectation for membership. Okay. But you will say, hey, that would be great because then I will have a dynamic hash table that is able to support insertions and lookups both in constant time. In the worst case, wrong. I can tell you now, this is something that will be very good to know. Okay, in computer science, nobody knows how to build a dynamic perfect hashing table that can support simultaneously insertions in constant time and lookup operations in constant time. One of them will have to be in expectation according to the state of the art. You see what I'm saying? And therefore, if you build a normal hash table, something you will learn from an undergrad course, right? Data structure course. And then you will get insertion, you will be able to build a hash table in n time. And this n time holds in the worst case. But the lookup time will be constant in expectation. All right. So that's usually what people do. Okay. If you want to do dynamic perfect hashing, the lookup time will hold in the worst case, right? But the insertion will have to become, expected. You see what I'm saying? Okay. All right. Good. So, hey, hello. Hi. It's okay. I'm recording the seminar. So hopefully I'll be able to release it. So this is something I'm going to need. All right. So now to summarize what I just said, insertion, you are able to do constant time in expectation, and the lookup time. Lookup means membership, right? This is a constant in the worst case. Okay, in the worst case. All right. So this is a data structure I'm going to need. Is that all right? Okay. Good. Now let's go back to phase one. Now remember the target of phase one is to produce a random permutation of n by 2 elements. Okay. You can imagine, this is set S, right? It has n elements, right? Eventually, we will produce a sequence of n. But in the first phase, we will produce the first half of the sequence. Okay. But it's important to make sure that the first half you can imagine the first element is randomly chosen, and then the second element is randomly chosen from the remaining elements, n minus 1, and then the next is randomly chosen from the remaining n minus 2, and so on and so forth. Otherwise, this would not be, otherwise this will not be a random permutation, right? Good. Okay. All right. So this phase goes in iterations. Okay. So in every iteration, I'm going to produce one element. Okay. All right, so the first iteration is fairly easy. Now remember, I have 3 bullets, right? So I have this sampling algorithm to help me, right? So it's a black box. I just call it, right? So you sample, let's say E, right, from S, right? So this takes how much time? This takes lambda SAM. Okay, you can think about lambda SAM. It's a constant if you want. So this takes a small amount of time. Okay, good. So this counts as the cost of iteration 1, right? But not only this, all right, so I'm going to add this E to as syn, all right? So this is a separate set that I'll be maintaining. You see what I'm saying? Okay, so basically you can imagine that as syn is empty because you have seen nothing yet, right? But as you go, I will be producing more and more elements in the permutation, right? So so some elements have already being seen, right? So you don't want to produce the same element twice, right? Iteratively. So that's why I'll be maintaining this as seen, right? Okay, so this is the reason why I need the dynamic perfect hashing table structure. Okay, so I will be um, maintaining a dynamic perfect hashing structure on this SC. Okay, so if I say, all right, now if I add this E to SC, what is the cost? And then you should tell me it's a constant in expectation. All right, so this is uh, what I explained before. All right, okay, good. Now this is the first iteration, and the first iteration is fairly easy, correct? Okay, good. Now let's look at things iteratively, right? So let's say the second iteration, right? So what do? You sample, again, you sample an element from S, okay? But different from the first iteration, you cannot really output this element right away, right? Because it's possible that this element has already been seen before, right? So how do you check? Well, you have this lookup functionality there, right? So if E is in S scene, right? And then you go back to the you go back. So you have to take another element. You see what I'm saying, right? So if E has not been seen, and then you output. Okay, you output this E. All right, you output this E. Oh, by the way, I forgot to say output, right? In the first iteration, but I think I did mention every iteration will produce one new element, right? Okay, anyway, so this is the second iteration. In other words, the second iteration within itself, right? There might be more than one loop. You see what I'm saying? Okay, it's possible that the element has been seen. And then in that case, you will have to take another element and you repeat this until you really get an unseen element. Is that all right? Okay, good. All right, so you do this for n over 2 iterations, right? So I think it should go without further proofs that so far so good, right? The first n by 2 elements are indeed randomly permuted. Okay, so strictly speaking, I owe you a proof, but unfortunately, you're not getting it today. Okay, I don't have time for that. But this should be very, very intuitive, right? I will even make a step further by saying, this is quite rudimentary to show that, the first n by 2 elements are fine. Okay, good. So this is what you do. All right. But let's worry about the time. Okay, let's worry about the time. All right, because I want to prove that the first phase. Actually, I want to prove that every iteration will have a small amount of time. Will run for a small amount of time. Will run in small amount of time in expectation. Right. However, there is a little bit of uh, issue here. The issue is that starting from the second iteration, you might have to perform multiple loops. You see what I'm saying? Okay. So somebody would say, if you are not lucky, you could get stuck here forever. Okay. You keep running into something that you have seen, right? So you won't be able to proceed, right? Well, this person, has a point. Okay. But of course, I cannot let such an argument bother me, right? So how would I be able to proceed from here? Okay. So there's one thing that you can notice, right? So I said phase one will last for only n by 2, okay? And there's a very, very important reason for this, okay? So if I did not have this requirement, and then yes, I would have run into some sort of trouble, okay? So if I say the first one, continues only for n by 2 iterations. Now, what does that mean? It means that this S scene, right? Even at until the end of phase one, what will be the size of S scene? What will be something you can claim? You can claim that during the first phase, right? S scene. I mean, you can see you can have seen at most n by 2 elements at any moment during the first phase. See what I'm saying? And therefore, if you look at each iteration executed during the first phase, what can you say about the probability that you will see something that you have not seen? You see what I'm saying? So if you look at every loop, think about it as tossing a coin, right? So this coin, if it comes up heads, and then it means good. You have you have sampled an element that you can use. If it comes up tail, it means it's no good. You have to do another toss, right? You have to throw the coin for another time, right? So this coin comes up heads with probability at least 1/2. Okay, it can be greater than 1/2. All right, it will be exactly 1/2 at the end of the first phase. Actually, it will never be exactly 1/2 because we will be running exactly n/2 iterations, right? So it will be very close to 1/2 at the end of the first phase. Okay. So in other words, how many loops do I have within each iteration, right? So the answer is in expectation, it's 2. Okay, in expectation, it's 2. Good. So if that is the case, and then you also have to analyze what is the expectation of one iteration. Okay, now remember, right? So sampling time is easy. Sampling time is a constant in the worst case. All right, so no questions about that. For lookup, it's slightly it's subtly complicated in the sense that you cannot say look. Did I say lookup? Yes, I said lookup, right? So lookup is constant case, constant time, so no problem with that either, right? However, you also have to do insertion, right? Insertion, you do it only once. You see what I'm saying? All right. You don't really do it for every loop, right? So therefore, if you think about it, it's like, for every loop, you will be doing constant time in the worst case for every loop. And therefore, you can say, since the number of loops is just a constant, it's actually 2, right? And therefore, the total amount of time of those loops will be constant in expectation. And then plus another expected term, right? So this is the term that you pay for doing the insertion. You see what I'm saying? And therefore, now we can conclude that every iteration runs in constant. Sorry, did I say constant? I kept saying constant. This is not entirely correct. I should have said, this is a lambda sem, right? Because you pay a lambda sem here, right? So it's basically lambda sem, right? Because the other operations are constant. Okay. All right. Good. So this is this is the first phase. Okay. This is the first phase. So every iteration does lambda sem in expectation. Okay. Good. All right. Nice. Now this is the phase number 1. Okay. By the way, if you look at the small delay requirement, right? In the first phase, I have been doing fine, right? Because if lambda sem is constant, this is a constant, right? In any case, I only promised the small delay of lambda rep plus lambda sem, and so far we are okay, right? Okay. Now let's look at phase 2. Now phase 2 is going to incur a long delay. Now, this is a heads-up message. It's going to incur long delay. Okay, so that's why this is not the ultimate solution we want. All right, it's going to incur long delay. In fact, in phase 2, I'm not going to produce any new element at all. Okay, I'm not going to produce any new element at all. So first 2 will simply retrieve the entire S. I will retrieve the entire S. So how much time does this take? Well, this takes actually n times lambda rep. Okay, so this is the second operation that is given to you. Okay, so I apply the second operation to retrieve the entire S. Okay, I don't have to know the details of this because, as I said, the second bullet and the third bullet, they are given as black box algorithms, right? So for acyclic joins, think about this lambda red to be a constant. So basically, I say I spend constant time producing the entire S. Is that all right? Okay, good. All right, and I don't output anything. Okay. However, I will compute S slash S sim. Okay, so basically in English, this is saying I want to get all those elements that I have not seen. How many of them? Precisely n/2. Okay. And since I can do lookup in constant time, I know that the second phase, or maybe the second step of the second phase will take no more than n time. Okay, good. So if you look at phase two and as a whole, and then I say phase whole will run in, I would just say c times n times this lambda ref for some constancy, which I know definitely exists, even though I don't need to solve it, but this C definitely exists for every black box algorithm. Okay, good. So that's phase two. So you can see that phase two outputs nothing, right? Long delay. How long? Wow, this is n. The delay is n. Actually, n times lambda ref. Okay, so this is pretty much the worst you can hope for. So so this if it was a small delay algorithm, the algorithm would have failed right here. Okay, good. All right, but that's okay. Let's continue. So you see, I still owe you the second half of the permutation, right? But now everything's easy because I have already got this S/S scene, right? So I have already got the n over 2 elements that have not been output yet, right? So I simply randomly permute this S scene. Okay, you know what? I will include this step into the second phase as well. So the second phase will also do this. Okay, and this is something I talked about before. This was discussed in a seminar that I gave in the first term. You can do this using linear time. All right. So if you combine 3 steps, these 3 steps in total take you c times n times lambda rep. All right, no problem. Okay, so that is the end of the second phase. Okay. All right, so phase 3 basically says, now everything's easy because you have a random permutation of the unseen elements, right? So you simply output the unseen elements one by one, right? So if I say, what is the delay that you can achieve in phase 3? Wow, you will say, the smallest you can get, right? So this is constant each time, right? Good. So that is the whole solution 1, all right? Now let's look at the solution 1. Well, first of all, it's correct. No problem about that, right? And also, if you look at the issue is in the second phase, right? The second phase has a very long delay, all right? Nothing is output, okay? Good. But overall running time, overall, in terms of amortized running time, okay, that looks fine, right? So if you look at the total running time, this is basically n times lambda sen, that's the total running time of the first phase, and then plus n times lambda rep, right? So that is the time of the second phase. You see what I mean? In other words, if you think about the amortized time per element produced in the random permutation, that looks fine, right? So that's lambda rep plus lambda set. Okay, good. So now here comes the big question for today, right? De-amortization. You see what I'm saying? How can you turn something like this into something that holds in the worst case? All right. So this is the moment that I said, right? So before I show you the solution, you'll be wondering, okay, how's that possible? You see what I'm saying? So now you have something that holds in terms of amortized cost, but clearly it doesn't hold in terms of worst case, right? But now I want to turn this into something that holds in the worst case, right? Exactly this algorithm basically. However, I will do a little bit of I would say modification somewhere, some magic, but then now you have this bound holding in the worst case. Okay, so I will give you solution 2, and the solution 2 will give you the entire permutation. Now this time promised. Okay, every time I output something, you will have lambda rep plus lambda sen in expectation. Okay, by the way, this is in expectation because the amortized cost is also in expectation. You see what I mean? Okay, but if the amortized cost holds in the worst case, and then the reduction will preserve the worst case guarantee. Good. All right, now, so let's get to the this de-amortization technique. Okay, so think about the three phases. Okay, so I'm going to draw the timeline for the three phases. Okay, so in the first phase, we do n/2 iterations, right? So for every iteration, we do lambda sim. Okay, and for the first phase, this is the total amount of time. Okay, so yeah, let's put big O here. Now for the second phase, we basically report everything, right? So the cost is dominated by this step, right? So I report everything, right? But in the second phase also does something extra because it will isolate the unseen elements and also permute them, right? Okay. Now, finally, the last phase is very easy. The last phase, you simply do you simply output the remaining n/2 elements, right? So I write n/2 instead of n to emphasize that you only have n/2 elements left. Okay, big O of n/2 is same as big O of n. Okay, all right. But just to remind you, I have n/2 elements left. Okay. So in terms of delay, the third phase is fine. Okay. In fact, I'm not going to touch the third phase. The magic happens in the first two phases. Okay. So if you think about it, in the first phase, we are reporting n/2 elements. Okay. Think about the first phase, right? I perform n/2 iterations, right? So think about every red interval here. So every red interval represents the timeline, the time duration of one iteration. You see what I mean? So I have n/2 of them. Okay. But for the second phase, there's no red interval. You see what I'm saying? Okay, because there's nothing reported there, right? So if I say what is the length of every red interval in the first phase, you should be telling me that's lambda sim in expectation. That's a lambda sim expectation. Think about this coin tossing argument that I gave, right? So okay, good, very nice. So this is the big picture. Is that all right? Okay, good. Now where is the trick? Where is the trick? Okay. Well, I hope this picture will be imprinted on your minds forever. Okay, because you will see the trick basically comes from this picture. Okay, what you are going to do is to increase the length of the red interval purposely. Okay. Now think about the following. Okay, think about having green intervals, still n/2 intervals. I'll be drawing. n/2. Okay. By the way, how many red intervals do you have? Once again, it's n/2. Why? Because the first phase performs n/2 iterations. And what does each iteration do? Each iteration will output one new element. Okay. So far, so good. All right. Now, I want you to think about this picture. Okay. The green interval. Okay. So you will see that I have precisely n/2 green intervals. Okay. Now, what does each green interval mean? It means that I will output a new element only at the end of each green interval. Okay, all right. And then if you compare the red intervals with the green intervals, what do you see? You see that green intervals are sort of like covering the red intervals. You see what I mean? All right, good. And the second thing you want to know is, well, what do you mean by outputting an element only at the green interval, right? You have already computed them, right? In the first iteration, you have already output them. Okay, so what do you mean you output them only at the end of the green interval? Well, exactly that's where the magic is. You have computed the elements, but you do not output them right away. You stash them, you buffer them, okay, however you like to call it. Okay, but the idea is you can look at the red intervals, right? In first solution, in solution one, right? Those elements are produced much quicker than what I really need in the second solution. You see what I'm saying? Okay, so as you go, imagine, right? The first solution keeps producing elements. right? You do not output them right away. You store them. You have already got the sequence of elements in your background, but you don't present them upfront on the stage. You see what I'm saying? You store them and you buy yourself some time. Why? Because you want to achieve the green effect. You want to say that, I would like to produce these n by 2 elements, at such a pace, such that, by the end of the second phase, I will have produced exactly n over 2 elements, so that I can go into the third phase, because the third phase is perfectly fine. Okay. All right. Good. So that is the idea. Okay, that is the idea. Now I'm going to present you with the details, right? But details are can be conceiving in the sense that they give you the wrong idea that this seems to be something complicated, but it's not, right? So it's really just implementing what I have said, right? So once again, the reason why you're able to do this is that, once again, okay, the length of every green interval is longer than the length of each red interval. If the other way around, you won't be able to do the magic. You see what I'm saying? Okay. So you'll be reporting, solution one will be reporting elements faster than what we genuinely need. Okay, so that's why you're able to buffer things. Okay, good. All right, so this is the idea. Okay, so the idea says the following. So in the first phase, now let's look at first phase again. All right, so we still do iterations. Okay, iterations 1, 2, all the way to n by 2. Same as before. The only difference is that I do not output an element at the end of every iteration. I did not say I will not produce. I will still produce one element in every iteration, but I do not output them. You see what I'm saying? Okay, good. Now, every time an element E is produced, okay, we append E to, let's say, a buffer. Okay, so at all times, I have a buffer. So this is a sequence, and this contains all the elements that I have already produced, however, not yet output. Okay, good. Now, in the first phase, I define this alpha. This alpha is something that might look complicated to you. All right, but as I said, you don't have to worry too much about how this alpha was calculated, because once you have got the main idea, you do the math and you will come up with the same alpha. Okay. So anyway, what you do is you will output an element. Now this time really outputting, okay, but from the buffer. Okay, from the buffer after every alpha iterations. So that completes the description of phase one. Okay, so once again, if you do not mind the output part, phase one runs in exactly the same way as before, except that the elements that you produce are appended to a buffer. You see what I'm saying? Okay, now the output part. I define this alpha, and I say, okay, now from the buffer, every time or I should say, I'll be counting the iterations. So the first element that is produced is output. So I should say the first element I output, okay, is done at iteration alpha, and then the second element output is done. The second element is output at the end of iteration 2 alpha, and then 3 alpha, etc., etc. Right. So if you look at this alpha, you can see that it's at least 1, because you have this ceiling there. You also have this 1 plus there, right? So basically, this is I would say at least 2, right? At least 2, right? So you'll be doing things slower. So that's what I mean by the green, right? So now I can even tell you what is the length of the green interval, right? So the expected length of this green interval will be alpha times the length of the expected length of a red interval, because you have alpha iterations there. Okay, you see what I mean? All right. If you look at the length of a red interval, that is the expected length of one iteration, correct? Okay, but every green interval, right? So I output an element every alpha iterations, right? So the expected length of one green interval is alpha times the length of one red interval. Okay, good. All right. Very nice. So that's what you do. Okay. All right. So now if you do this, okay. So let's draw the picture in a better way. So here you will be having alpha iterations like this. Okay. And then I'm going to give you, say, Brown intervals. Okay, so I will apply the same idea to cut the second phase. Okay, except that strictly speaking, the intervals that you get from the second phase do not need to be of the same length as the green. All right, so but the main idea is the same. Okay, so so to give you an idea why this works, okay, even though this is part of the detail, right? So if you think about it, I have n/2 iterations in the first phase, right? And now it's like I will output something after alpha iterations, right? So compared to solution one, which outputs an element every iteration, right? So I will be outputting just 1/alpha of the n/2. You see what I'm saying? So before phase two starts, I have a large number of elements still in the buffer, right? Because I definitely have produced n/2, and I have output n/2 divided by alpha. So I still have n/2 times 1 minus 1/alpha. So that's how many, correct? Good. Now, intuitively, in solution one, right? Second phase, this phase number 2 was entirely silent. But now, since I still have a lot of elements in my hands, I can use my elements to pay for the silence now. Okay, so now things become really, really easy. So you have C times N, C times N times lambda rep, for the maximum duration of the second phase, right? And I still have so many elements in my buffer, right? So now I want to pay for the silence in an even manner. You see what I'm saying? So I will decide the length of this Brown interval like this. So this is precisely the length of every Brown interval. Okay, so there's no even amortization. There's no even expectation here. Okay, good. So as I said, right? So I will only touch phase 1 and phase 2, and phase 3 I won't even touch it, right? Because phase 3 was perfect, right? So it doesn't have to be touched. So overall, if you look at the overall delay, right? Because delay will have to hold everywhere, right? So basically, it will be the maximum between the green and the brown, right? So when we say maximum, asymptotically speaking, is simply the same as plus. You see what I mean? A plus B, right? Big O of A plus B is just the big O of max of A between B, right? So basically, it's the delay of the green interval. So this is from the first part. Now don't forget, right? So every red interval has the expected duration of lambda SAM, right? So every green counts alpha iterations, right? So this is the expected delay in phase one, right? So we also have to consider the expected delay of the second. Okay, all right, good. So I'm not going to do the rest of the derivation, but now if you plug in the value of alpha, now alpha is not necessarily a constant, right? Alpha depends on the ratio, okay? But if you plug it in, right, and you simplify everything, and then you will be able to bound this as I claimed. Okay, all right, good. All right, so this is the end of my seminar.